we already have considered a case of a spring mass system when we said that if we have a spring mass system such that the mass has been stretched by a distance x, and if you further displace the mass or stretch the spring by a small amount dx, we said that work done is F times dx, and F is nothing but kx. As you see, the force applied to stretch the spring is F, which is kx, same as the spring force, which is minus kx. So spring force is just in the opposite direction of this mass. So if you make a free body diagram, actually this is how it looks. Right? And they are both the same. They have the same value because the mass is not accelerating. We are moving it slowly away from the central point. So if you apply a force F, the spring applies the opposite force kx, but there's no acceleration on the system, and this mass is sort of very little more than kx, so that it keeps moving the mass forward. And when it moves with the distance dx, the amount of work it does is fkx, and this negative sign tells that the spring force is in the opposite direction as the external force. This is external force. Because you can also say a little more. We are talking about here how work is done. We are not really talking about what is the acceleration of the system. There is no acceleration in the system. Just F external is little more than kx, so that it keeps moving the mass forward. And if it moves the distance by dx, then this is the amount of work it does. So we are talking how to calculate. This all comes under the topic of differential calculus. So you need to have a little understanding of differential calculus to understand what's going on. But the idea is that the amount of work done by an external force is f dx, f external times dx. And this is nothing but that. So, and also this is the small amount of work done. And if you want to find the total amount of work done, let's say going from x initial to x final, then work done is half kx square xf square minus half kxi square. Just we integrated that to get the two from here to here. We integrate. Okay. Very much similar to this is the case when we have a planet, or let's say Earth, and at a distance r, from the center of the Earth is the mass m. The force of gravity, we know according to Newton's law, is g m e. M e is the mass of the Earth, m over r square. This is fg. Now if you move this mass from here to a very small distance up, so that r sort of stays constant, then we can write this as g m e m over r square dr. This is the work done, same as the previous case. And if you go from ri to rf, you can write w equals, just integrate that, and this gives you g m e m, and the bracket you get 1 over rf minus 1 over ri. This is what you get. Okay, so let's see if this is right or not. 1 over rf is a smaller value. Well, actually it should be minus 1 over rf and plus 1 over ri. When you integrate, you'll understand how this, but this is the final formula. And this is the work done by the force. So you're applying a force on this mass m, so that it moves from here to here, similar to the case when you apply a force external, F external, so it moves from here to a distance dx. So you apply a force F, up, external, to move the object from here to here against the force of gravity. So in the last case, it was spring force that was a restoring force. In this case, it's the force of gravity that is the restoring force, trying to restore it to towards the center of the earth. Okay, so this is the work done, or increase, you can also call this increase in gravitational potential energy. Okay, because work done should go increasing the potential energy, because we can really understand that this mass has less potential energy than any mass which lies here, because uh, there's an increase in the height of the mass. Anyway, so this is the work done, or increase in potential energy. Okay, and this is called gravitational potential energy. This is gravitational potential energy. But we have all the time been writing that the change in gravitational potential energy is also written as mgh. This is the change, this is the difference between the gravitational potential energy of a mass m at a height h. So energy here, the difference between energy here and energy here, this is h, is nothing but this. We have written this also, that this is PE for gravitational. So how are these two same? Well, they are not the same actually, but this formula reduces to this when we talk about potential energy near the surface of the earth. So this is only valid, this is valid near surface of earth. Let's see how this is happening. So we said work done by an external force is given by GME m 1 over Ri 1 over Rf. I keep forgetting the signs, but I think this should be plus and this should be minus. Okay, so if we are at the surface of the earth, which means let's say Ri is same as Re, which means we start here and we end here. So this is Re, and this guy here, let's say, is Re plus H. So you can write work done or increase in potential energy, the same meaning. Whatever work you're doing is going increasing the potential energy, equal GME, should be actually capital E, M 1 over Re minus 1 over Re plus H, right? Because this is Re and this is Re plus H. Okay, and you can write this as GME M, and in the bracket you can say Re. You can add the two fractions to get something like this, right? Okay, and also you know that because Re is much bigger than H, you can write this guy as Re squared. So that gives you GME M, well, close to, very close, Re squared times H. And you might have identified by this time this is nothing but small g. So this is nothing but mgh, which is nothing but is the potential energy near the surface of the earth. So near the surface of the earth, this potential energy formula can be written as mgh, or the change in potential energy can be written as can be written like this. Just to recapitulate, the potential energy, the gravitational potential energy, you can say gravitational potential energy is written as GME M divided by RE. This is the gravitational potential energy. Well, actually, there's a minus sign. Okay, and this is because of the way we define Fg to be GME m over RE square. And that's why this is written like that. Okay, and you notice this is a negative number. That the gravitational potential energy is a negative number. And we'll talk about that in the next lecture.